And you will talk on modeling the graph of Tyndall stars.
Okay, thank you, Donatella. So for those of you who don't know what Tyndall stars are, I'm just going to start by showing you 3 videos which were done in Oxford a few years ago by a student there, Matt Hennessy. So quite a few of these growing at once, a bit irregular, but each one of these objects is a Tyndall star. So what you can see here is mainly ice. I'll show this one again. Now, oops. It's mainly ice. This is a fairly flattish piece of water. Trying to ignore these round splodges, which are just water vapor bubbles formed because the water is a bit more dense than the to escape from here and show you another one if I can. Close this. So most of this is ice. What we have here is, not one of this, yes, it's one of these things. What we have is a overhead projector with a slab of ice, fairly pure ice, and the light from the light projector has been shone on it, which is causing the ice to melt.
What is this thing moving?
Yeah, so I'll keep showing them. So most of this is ice. Here is a thin bit of water, and this thing bobbling around, which you're trying to ignore because it's not very interesting, is actually a water vapor bubble. As the ice melts, it contracts a bit, so it leaves some space which is filled by water vapor. So it's just formed by change of density. So it's very visible. But trying to ignore it. So what you see, you can tell that these things are quite flat, which is the thing I'm going to concentrate on today. Eventually you want to try and build essentially a 2D model, more or less 2D model, and once that's done satisfactorily, which you haven't really got to yet, then concentrate on the formation of the hexagonal and branch structure. I'll do one last one, which is, oops, I didn't mean to do that, let's close it anyway, and go to the last one.
For a moment, it looked more like the formation of dendrites.
Yeah, well, they are dendrites.
But somehow then you think
So, oops, I do that. That's the trouble doing backwards. Getting what I was doing. Try again. See if we get the right place this time. Yep. So this one is this one appears staying nice and stable.
So what is water and ice?
So the main bit,
Water is increasing.
the water is increasing. So we've got ice around here, and we've got 2 levels of water. So you've got one bit of water, another bit of water at a different level. Both are expanding, one behind the other. And there are some more up here. There are 2 or 3 overlapping each other here, and these are staying fairly circular, not showing much instability, although one of them actually is now. And yes, we've got the hexagonal structure, and one last time.
so.
water moving into ice creates dendrites. This is what
Yep.
you see,
Yes.
Amazing.
which is not what we thought.
No, it's the opposite, we thought.
So, no. So, remember what's going on. The basic mechanism here is it's body heating. So what we've got is hot ice. It's not warm water propagating.
Yeah.
So it's the same. It's not. You're used to thinking of dendrites as being from, say, supercooled water. This is superheated ice, which is really then much the same thing, which is why you've got the instability. So it's the same instability, but the question is, can we build a simpler model which also takes account of this very flat 2D structure which we have here, and that's what I really want to speak about today, well, main gist of today's talk. Really, it is quite preliminary work in a way, just try to think about the sort of models we'd be wanting to look at. Right, now. Where is it? Full screen. Okay. So there's me. So those videos were just done by Matt Hennessy, who's now a PhD student. I think he was just an MSc student at the time he did them. He's mostly working on other things. So he's mainly a maths student, but he does some experimental work as well. Richard Katz is his sort of practical supervisor in the Department of Earth Sciences, I think, at Oxford. And John Lockinen, my other supervisor, sort of link person who's sort of gotten me interested in the problem. So Tyndall stars, other name, I think you might have seen why now, is liquid snowflakes, because snowflakes are solid objects and they have this hexagonal structure. These are liquid things and have an hexagonal structure. Also, both are fairly thin objects. Tyndall, don't know much about him. He wrote a paper in 1858, and he observed these by, I believe, by concentrating probably sunlight on alpine snow. I don't know if it's important it was alpine, but it was alpine ice he would be using. I have one paper by Takea in 2006. He did some experiments, those were performed by carefully raising ice to very slightly above 0 degrees C, then introducing a deliberate nucleation site and seeing what happened. So it's quite small pieces of ice he did. So it's a few millimeters by a few millimeters, and when you did low superheating, and by low superheating means something under 0.05 degrees, what you saw was when you looked sort of from the top, now I'll be careful what I mean by on the top, so you saw there were thin, because you could see there were different layers. We have one preferred direction and then two other directions. The preferred direction, or the direction where nothing much is happening, called the C-axis. So there's not much melting going on the C-axis. So there's finite thickness in the C-axis, which I'll take as the Z direction. So in the X and Y direction, you just see a disk. There's no sign of instability for this low superheating. High superheating, so that'll be over 20th of a degree, then there will be some instability. Also, when you have this low superheating, if you looked at the thickness, his paper gave plots of thickness against time, and all he gave was a plot like that. It just leveled off. And I think the reason for that was there just wasn't enough heat in the sample for it to keep going. When you had more heat, not only did you get the instability, but the thickness just kept growing linearly. Oops. Now, these some more recent experiments carried out by Matt and a summer student being undergraduate in Oxford in the Department of Earth Sciences there. And just a quote from his recent email to me, there's 4 power regimes will be rather probably vaguely categorized, but just to say what he said. So low power, roughly equate to the lowest superheating of Takea. You just see, viewed from the top down in the C direction, just a circular profile. Then, with a bit more oomph, then you'll see the hexagonal structure, and you start to get more instability the more and more heat you put in. So, some sign of instability. Oops, wrong way. First you get hexagonals, then high wave number, corrugations, instability in other words, then a flower shape, strong 6-fold symmetry, and then the dendrite structure, as pointed out earlier. Okay, so we have some stills here. Matt also sent me some fairly classical photographs of paper in 1956 by Nakaya, just in case of any copyright, because this talk being videoed, I thought perhaps I shouldn't put them in. But the low power one, there's not much to see there. What it was a circle with the usual vapor bubble in the middle. So that was low power. The medium power there, you see, well, there are the corrugations, but they're pretty small, and you do see that otherwise it's fairly regular, and there's a bit of the hexagonal shape. And of course, there's the usual water vapor bubble, which I want to ignore for present purposes. These are the high power, supposedly. So this was older one by Matt himself. A nice sort of petal shape, and not much in sign of instability there. No rapid wave number sign, whereas this one has quite big dendrites, I might say there, and the very high power one, recently done by the summer student Harvey. A couple of years ago, they were doing some better. So I should say that these 4 pictures were all done again with things like that. Getting an overhead projector light, just focusing the beam on the ice. So it was done with an incandescent light, just focused. So it's a bit hard to get good measurements of the power of the light. So a couple of years ago, they did some laser experiments where you know exactly what the power is. Unfortunately, their results were rather boring. Really, all they saw were things like that. So looking down from the C-axis, all you would see was a circle, just a disc from above. From the side, you'd see something lens-shaped. You'd see something which is this profile here. So the basic physical model I've got for this cross-section, the C-axis, or the Z direction, it will take us vertically, and this horizontal direction will be the XY plane. And most of the time we'll be looking at sort of axial symmetry. So rather than think X and Y, I'll be saying everything is just function of Z, R, and time t. So all that's going on in their experiments will be body heating from the light, laser light for their control experiments, which are rather boring but well controlled, incandescent light for their overhead projector experiments, but less well controlled, usual heat flow, got a free boundary, ice outside, a lot of it, thin region of water. The physics is much the same, the numbers are slightly different, density is much the same, slightly different, which gives you the vapor bubble. The specific heat is rather different, thermal conductivity is rather different, the absorption for the light is rather different, but they're the same order of magnitude. For today's purposes, today's talk, I'll take them exactly the same. They will be slightly different, but they just complicate matters. So I'll regard everything as being the same value in ice and water today, although they are slightly different. Then, of course, we have the free boundary, gamma. Moving with velocity v, normal n. So we have the usual Stefan condition. And the key thing, we think, to give us this preferred direction is going to be anisotropic kinetic undercooling. We'll probably ignore generally any Gibbs-Thompson effects, although it probably will be vital for a bit of rounding now and again. So that will say that it's going to be much more reluctant to move, or they'll give some reluctance, shall we say, to move in this direction compared to these two directions. And that will then depend on so this kinetic condition will have something to do with this angle psi between the normal direction and n and the z-axis. So mathematical model is essentially what you'd expect. Just a standard heat equation with the source term, as long as we're away from the free boundary. Let's say the normal Stefan condition at the free boundary, and then we have this kinetic, well, I tend to call it undercooling, but of course it's overheating in this context, with constant k, and also there's this anisotropy term f, which is to do with the angle psi. Now, one of the problems, many problems with this problem, is even without anisotropy, although we have a good idea about the rho, the densities, the specific heats, the thermal conductivity, and at least for laser experiments where we know what the light is doing, we even have an idea what the Q is. There don't seem to be much in the way of physical measurements of what K is, let alone what the F might be. But we'll proceed on the assumption that K is in some sense small, so that the kinetic undercooling is playing a role, but somehow it's, under normal circumstances, it's small. It's there, but it should generally be small. And these, at least for the laser experiments anyway, which perhaps is what today's talk is really based on, with very small inclusions, we've got small bits of ice, small bits of water in large region of ice, so we'll have a condition at infinity, so we're just saying that everything's nice and uniform at infinity, so just T is behaving, the temperature T is behaving as QT over rho Cp at infinity.
V is the speed of the free boundary?
V is the speed of the free boundary, yes.
So the new thing is this second T is equal to kV thing.
So big T is the temperature, V is the, so
And the new thing, the difference between Stefan model and this one?
so the normal Stefan model would just have T equals 0 here. Then normal undercooling condition would have KV here. and nothing. This wouldn't have this f function. So what f will we take? We want to get this just this asymmetry between z and the other directions. So we want this psi coming in. So essentially it'll be doing something like this. So normalized to have a maximum around about 1 when psi is pi over 2. So that's the wrong way again. So that's around about here. That's the preferred direction for it to travel. And going upwards, it's a bit reluctant to go. That's psi equals 0. We'll take this to be some small epsilon, or something like epsilon. And not do anything strange, so probably monotonic in between and leave periodic. To get a simpler looking model, get rid of all the constants, there's some obvious scaling. To get the latent heat out, scale temperature like so, then to get the source term set to 1, scale temperature so, and then set diffusivity to 1, scale distance with the rather awkward looking square root. So simple looking heat equation. Stefan condition is simpler, and then I've written now the kinetic and cooling law with the F on the other side, and this lambda here, that lambda for so-called small undercooling, this lambda will be large. So at the moment we're thinking this lambda is being large. Unfortunately, if you do it this way, the dimensionless temperature we're choosing to scale with, that's this L over Cp, is 167 degrees, whereas we're thinking a fraction of degrees. So this is ridiculously large. This is ridiculously large time when we're thinking about seconds or smaller. And this is centimeters, we're thinking about millimeters or smaller. So everything is far too big at the moment with the present scaling. So somehow we should be bringing in this lambda in, or maybe the anisotropy, which is sitting inside this F. But certainly the obvious scaling is rubbish. So we want to bring this lambda in. Also, what sort of F should we be thinking about? Well, some material scientists have looked at bubbles for snowflakes, just looking at the two-dimensional behavior in the x-y direction, and the sort of F they've looked at there has been something of this form here with a cos squared of 3 psi. So this gives us the 6-fold symmetry. So an obvious choice for us with the psi's I've got it would be this thing here. So this will be a standard choice. So we're going to have choose anisotropies like this, and we'll be looking at other ones as well. Epsilon is small and lambda will be large, and we'll have a revised, yeah.
So this comes from the inner structure, molecular crystal structure.
I have no idea, to be honest. So where they got this from, where the material scientists got
This
them.
goes to be hexagonal or something. It depends on the
Yeah. So they would have. They need something like this to get the hexagonal structure. Yes, but there will be other choices which would give an hexagonal symmetry. Just as there will be other choices which are this, which will give our 2-fold symmetry. So if we choose our rescaling like so, well, we bring in a revised diffusivity, I'm afraid. We bring in a number we bring in a small parameter into the Stefan condition. And just for present purposes, to make things sort of look nice, I'm assuming that there's a distinguished limit between this large lambda and this small epsilon, of lambda being of size epsilon to the -3/2. Just to make this retain heat equation here. If this big lambda is large, we'd get a Laplace equation, which is fine. And proceed much the same, but I'm taking this distinguished limit for definiteness. Now, with this form of the free boundary conditions here, what we tend to see is that the thickness moving in the z direction, both from v equals this part here with the epsilon in, or from this term here, because psi will, from the form of this f, the thickness is going to be order epsilon now. Before we move on to, so go back to this, so thickness is order epsilon, whereas we generally would think of x as being order 1. This is going to give us order 1, this distance, x and y will be size 1, z will be small. We're heading towards a codimension 2 problem. All the action is going to be in a thin strip near z equals 0. Before we move on to that, I'm going to look at time, which is smaller than this time scale we look at now. Go the wrong way again. So here we're looking at a very short time where all our quantities on a revised scaling are minuscule. Our revised time tau is tiny. Theta is going up with time, with temperature, with time tau. Theta will be much like it. Distance is going because of the velocity being like temperature, which is a bit like time. Distance is a bit like time squared, except in the z direction where it's got the epsilon, that's even smaller, like epsilon times squared. Then we're doing rescaling. We essentially neglect everything and get to the Laplace equation of temperature. Stefan condition reduces to jump in temperature is 0. We still want temperature to be like time at infinity. So all it's going to say is that temperature to lead in order is time. Meanwhile, the kinetic condition is still there, and this then just says that the normal velocity is given by the time t times the anisotropy condition, the specified function times the angle, which is a form of the Iconian equation. The moment it's got the time explicitly, we can get rid of the time by change of variables. Set s is half tau squared. So our new velocity is then just a function of psi. If we try to get time as a function of our radial distance from the z-axis and z itself, well, sine of psi, cos of psi are easily written down. Then we can write our velocity v in terms of these partial derivatives, and we end up with this partial difference equation for our revised, our rescaled s in terms of r and z. So it's this nonlinear, it's this anisotropic Iconian equation. which in principle is easy to solve with Charpit's equations. We solve by following along a characteristic along which SR and SZ will be constant, and the form of them, S dot is 0, so S is our variable along the characteristic, and then R dots and Z dot we can get just by differentiating the mess of those functions. So in general it's rather messy to do, so I'll now look at some explicit forms, guesses for our isotropic function f. And we'll start off saying let's take it to nucleate from some tiny little nucleation site which is small compared to our epsilon. So I'll start off with a sphere, radius A much smaller than epsilon. So here's the one we first thought of, motivated by what people did with snowflakes. Turns out this one has some slightly unpleasant properties, which is why I've relegated to position B and consider this one, which is slightly messier, first. I'll take C as well, because just to bring in this 6th power, although it's still got the 2-fold symmetry rather than the 6-fold symmetry, well, it's got power of 6. And then this one here, so these three are sort of order 1 unless psi gets close to 0. This one here is order epsilon unless psi gets close to pi over 2. So to sketch them approximately, B look much as I first drew. A looks more linear. So A looks rather more linear. C is rather flatter and spikier, and D is spikier still, so it would be more like that. So that's roughly A, that's C, and that's D qualitatively. Right, so we just solve along the characteristics, and these are our plots. Now, to test how people are, I don't know if it's quite obvious what the limiting shape of those are. This one, the limiting shapes are what you might think they are. I don't know if the limiting shape of this one is so obvious. It might be what you think it is as well. So for small s, it is indeed what you think it is. That essentially there are two bits of the curve, two sorts of bits of the curve. Part of them are essentially, as I've got the cross section, they're semicircles, and the other bits are straight lines, so it's sort of sausage shaped. And then the other, for the larger s limit, we have these as being the profile. I don't know if it's obvious what profile those are. Any guesses? It is actually an ellipse. It's a disguise, but it's an ellipse. So as we approach order 1, so it's ellipse in cross section, so it's an oblate spheroid, the thing we're getting. Right, for B, is rather more unpleasant. We can still get the thing out exactly. The trouble is we get a corner happens at a certain time. If we continue blindly going away with our solution, we get multi-valued solutions coming out. So I think what should happen is we just cut off these bits here. If we put in the, say, Gibbs-Thompson, we clearly want to have some rounding about here, which would cut off these awkward things. So cutting off the corner, we get this sort of shape instead. I haven't drawn the C and D, but they're much the same, except they're rather thicker. So the growth in the Z direction all the time is like epsilon times squared. In the R direction, it's like times squared for A. But for the others, well, the anisotropy constant epsilon comes in. So we see that for B, it doesn't grow so fast. For C, it grows more slowly still. And for D, it actually grows the same sort of rate. It's a different numerical constant, but in fact, it's not thin at all, it appears, for this guess of the anisotropy function. So to get a thin Tyndall star, we've got to get the anisotropy function right. Okay, so let's move back to order 1 time and back to problem A, which had the nicer properties of the smooth solution. So all the action said in the Z was that confined to thickness epsilon. So the water is stuck near the Z equals 0 plane. So we solve heat equation away from Z equals 0. The Tyndall star or Tyndall shape is now confined to Z equals 0, and it's where R is less than some S of time tau. At the edge, we'll have H equals 0. The water region is now between Z is plus or minus epsilon H. So H is one of the things we want to find. H just gives us the thickness of the water region. So we're trying to find here the thickness H. We've put both the Stefan condition, here dH by d tau is d theta by dz, and the kinetic condition, d theta by dz is this thing here, onto now Z equals 0. So these two conditions here will give us the condition for theta and the condition for H along Z equals 0. The moment I've got two conditions at the edge, R equals S. H equals 0 because that's the front where the thickness is originally 0, and going back to the original kinetic condition, the S by d tau, which is the speed of this thing, equals theta, the original temperature. It appears from looking at the local behavior got from these conditions here that this condition is actually redundant, which is just as well, because when we look at the corresponding codimensional 2 problems for the other nonlinear, other anisotropies, we lose this condition because we have a corner there, so we have nothing corresponding to that for the other cases. So we haven't investigated this problem as regards well posedness at all. All we've done so far is try to do a local stability analysis just to see if there's any hint of the fingering which we eventually hope for to get us the Tyndall star eventually. Even that has been rather inconclusive. Looking at some local coordinates about the front, here now written as x equals ct, which will leave this point here, xi equals 0, and a perturbed front put forward times delta S1. So here is a local expansion of temperature using some local polar coordinates. All we eventually find is that the growth of the perturbation of the front is given by the linear part of the temperature field, or local linear part of the temperature field. That's this term here. Now, looking at the local part of the temperature field, well, C is the local temperature, which is positive. You have this usual sort of square root behavior. The coefficient is going to be positive. B, I conjecture it's positive, but at the moment I don't know if this number B is positive or not. My conjecture is B is positive, which will give instability, but well, I certainly hope it is, because I would like to see fingering to get the Tyndall stars, but I'm afraid until we can solve this problem with appropriate initial conditions, I don't know what B is, and I don't know whether this will give us fingering to give us the growth of the dendrites. Okay, so moving on to the other cases, supposing if we did have other anisotropies, and we certainly don't know what the anisotropy is, so let's just look at a case B. Well, we saw here that actually we had this different growth for over respect to time. It has epsilon half tau squared. So by the time this gets up to size 1, we don't have tau as order 1 anymore, we don't have the thickness is order epsilon anymore, so we have to do quite a different rescaling. So we get a slightly different problem, which means writing the thickness differently. It's thicker than it was for the previous one. Temperature is bigger than it was before. Time is bigger than it was before. So I've got a different equation, got the Laplace equation rather than the heat equation. Other things are much the same. Well, the anisotropy law on z equals 0 is a bit different, of course, because, well, it's a different law. And as I said, because we've got a corner here rather than this nice smooth object we had before, I've had to drop one of the conditions. So that's what we'd have if by any chance we had anisotropy B. C, well, let's spot the difference. Slightly different scalings for thickness, temperature and time, slightly, and of course different anisotropy law, but otherwise the model is much the same. If we had something like the Takaya experiment, where we don't have body heating at all, also what we've been doing so far has assumed that the nucleation has happened, the Tyndall star, Tyndall shape, is formed almost as soon as we've reached temperature 0. There's no reason why that is necessarily the case. We might have nucleation happen quite late on. If that does happen, and if it does happen that the time at which the water region forms is large compared to the original scaling, then our problem is slightly different, but not a lot. Again, variables mean something different. The biggest difference is the condition at infinity. Rather than have temperature is going up with time at infinity, is now just fixed. And what that will mean is then that if we look at our early time behavior, where temperature was going up with time, so velocity was going up with time, so distances were going quadratic with time. Now, of course, velocity is fixed, and so distances will behave linearly. And of course, this is what Takaya had with his large superheating in his experiments, that his growth, the thickness, was linear in time. Right, so I'd say this is really just looking at the preliminary stage of modeling to try and get at a codimensional 2 model, try and see if we can get some simple equations which might lead us to eventually look at some essentially 2-dimensional models for these Tyndall stars. Things still to do, well, the paper we've in preparation has looked at long time behavior. That is extremely tentative at the moment. We have some conjectures as to possible simulatory behavior, but simulatory exponent is quite open. We have some conjectures really. There is related behavior got for the plus equation, which John King was joint author of a paper some years ago, where there were oblate spheroids mentioned. So again, this thing might happen here. Depending on what the exponent is, the growth might be very much like the early time behavior. It might be like the Laplace equation, it might be something quite different. We really want to assign this B to decide on stability. We really would like the thing to be unstable to see if we're going to get Tyndall stars rather than these boring disks. We would like somehow to get a handle on the anisotropy function. And as I say, at the moment, there isn't the physics there. At the moment, all we can do is say, well, we'll guess these functions and see if they do the right sort of thing. And even some physical constants would be good. Without the anisotropy function, even without the anisotropy function, at the moment we don't know what the k is. And of course, having written down the codimension 2 problems, it would be good to start looking at some well-posedness of those. And I think I shall finish there. Thank you.
Any questions?
So these precise exponents, is there any confirmation that they appear there?
So the exponent, you mean as in the case A, case B, case C? Now all we have is he's now at Oxford as well. He's a really material scientist, John Wettlaufer. So I'm not quite sure. So he took that cube power of cosine. I'm not sure where he got that from. I think it was probably just because it gave the right sort of symmetry. As long as you took, and you could write that as simply as cos 6 psi or sine 6 psi, and so really is the simplest thing you could do, which has 6th fold symmetry. So likewise, for this model here, to get the difference between the Z and R, the simplest thing you do is what I had was model B. The only problem with model B is it gives you the corners, which is sort of why I don't like it mathematically. But I have no physical reason for getting rid of it in that way.